Hello friends, I'm Kavish Shah and this presentation is about our final project for the subject of Advanced Digital Design for DSP and Communications. Our project is basically parameterizable LMS Adaptive Filter. So let's start with it. Yeah, so in the overview of the presentation, it would be an introduction of the whole design procedure and the working of the LMS adaptive filter, the simulation and the MATLAB results for the implementation of this filter and the conclusion and future scope for it. The basic aim of this term project is to design a parameterized adaptive filter and to perform weight adaptation by using the least mean square algorithm. This presentation contains the theoretical background of how adaptive filters and the LMS algorithm work and also the simulation results. The motivation for this project is obtaining configurable parameters for design reuse such that a clean, noise-free signal is generated. The analog signals in nature are composed of an infinite set of points which are used to represent any data. However, any system contains of only a specific amount of bandwidth and memory which is not sufficient. So analog signal should be digitized. A filter is a device which helps in this discretization. A noise-free signal is the output from this filter. The advantage of using an adaptive filter is that it has configurable parameters. As the filter's attributes are parameterized, it makes the filter reusable. Let's go ahead. The description of the design. The usual method. The adaptive filter is a filter in which attributes are parameterizable. The four basic attributes are the input signals, the architecture that defines how input is converted to output, parameters that are changed iteratively to change the input-output relationship, adaptive algorithm that defines how parameters are adjusted over a particular time. Let's just go about with the basic architecture. As you can see from the diagram, it consists of a data RAM, coefficient DP RAM, LMS engine and the FIR engine. The LMS block and the FIR block are the main components. The data memory and coefficient memories are implemented as RAM blocks. The data memory is implemented as circular buffer to reduce memory traffic when long taps are to be implemented. Coefficient memory is dual port as each coefficient must be updated for new data. In the IP core of the adaptive filter, there are these two multipliers in the filter engine, one in the LMS module and another in the FIR module. The multipliers support bit widths of all lengths in the multiplier, multiplicator and the product as well. Also, the filter engine takes care of saturation and rounding of any numbers that exceed the length. The filter engine can be replicated again and again to implement adaptive filters of bigger tap widths. For example, 8 filter engines with 128 taps each can be combined together to form a 1024 tap adaptive filter, basically a 1K adaptive filter. Pipelining can be done so as to increase the system speed and performance. There is a drastic increase in performance when using many multipliers. Now for the filter, the usual method of estimating a signal corrupted by additive noise is to pass it through a filter that tends to suppress the noise by leaving the signal relatively unchanged. There are two types of filter, a fixed filter and adaptive filter. A fixed filter requires prior knowledge of signal and noise. It is possible to design a filter that passes frequencies contained in the signal. The fixed filter rejects the frequency band occupied by the noise. The second filter is the adaptive filter. It has the ability to adjust their impulse response to filter out the correlated signal in the input. It requires little or no prior knowledge of the signal and noise characteristics. If the signal is narrowband and noise is broadband, no prior information is needed. Otherwise, they require a signal that is correlated in some sense to the signal to be estimated. Moreover, it is able to adaptively track the signal under non-stationary conditions. As you can see from this block diagram, the adaptive filter mechanism, the filter coefficients are changed over time to adjust to the changing characteristics of any signal. The Xn is the input signal from any discrete source. The Yn is the output signal after filtering. The Dn is the desired output signal, and En is the error signal generated from Dn and Yn. The filter in the above block diagram can be an FIR or an IIR. So it can be a finite impulse response or an infinite impulse response. The weight adaptation block uses algorithms like LMS to change the filter weights. The working of the adaptive filter. As you could see in the above block diagram, the signals were mentioned, and the desired output signal is a product of the input signal and the filter coefficients Wn, which is actually Yn. The samples of Dn and Yn are subtracted to get the error signal, and as the index n increases, the magnitude of this error signal is supposed to decrease and the output matches better with the desired response. The adaptation process occurs over a time period of n to n plus 1 samples. Now this is the LMS algorithm flowchart, and in this flowchart, the weights are calculated by changing the previous weight and converging factor. The filter is adapted based on the error of at that particular time instant, and the algorithm can foretell what the next value of tap will be by adding an error value to the present tap value. The MSE reduces the correction. The gradient measures the closeness of the tap value. Next, we would go with the calculations. These calculations are shown over here, and for n calculations, we would require for n taps we would require at least n plus 1 cycles, and the inputs and the desired signals are filtered and are generated in MATLAB and given as input to the design. The operations of the LMS algorithm and the filtering takes place along with the delayed inputs, along with the multiplications of the coefficients which are generated by the LMS algorithm. It gives the signal which are added according to the taps. Say for example, for the 4-tap filter, 4 inputs are multiplied along with the coefficients to give the output, and all the 4 output are added to give the valid output. Next is the design tools. The requirement for our course was the design was first done in MATLAB to check the convergence of the error signal, and the Verilog implementation of the filter was done in the Altera Quartus model sim, and to verify its behavior. Here you can see the results from the model sim. This graph contains, this is actually the signal of our input, the Xn, and this is the desired input signal, and both of them we've taken around 1000 samples, and after going through the filtering, as you can see in the error signal, it probably converges around 275 to 300 samples. So this is how our LMS adaptive filter converges the signal. Here you can see these are our MATLAB graphs. This is the input signal and this is the desired signal, and here is the MATLAB graph for the error signal. Here also you can see that the error converges probably around 300 cycles, and that's how we got it. Let's go forward. So the conclusion, our LMS algorithm was used to get a better performance of the adaptive filter. The mean square error was minimized by using step size. As step size increases, convergence is faster. However, a loss in accuracy is seen as this value of step size becomes bigger. Another limitation is that the range of step size depends on some statistical attributes of the signal. A sinusoidal waveform was tested by using different values of signal to noise ratio. The output from MATLAB was matched with the expected output from the model sim. The future scope for this project would be to implement the functionality of the adaptive filtering on a FPGA, maybe on a Cyclone 2 D1 board, and verifying the error signal convergence. We could also the other futures scope would be that to implement an LMS filter for echo cancellation. So yeah, that's it. This is how we completed our project. Here is the biography and all the my name and all the details. Thank you very much.